So I've been trying to flip the classroom with Jupyter and GitHub. And so my goal is to teach mechanical engineers. So I'm a mechanical engineering professor. So my goal is teaching mechanical engineers who typically don't want to learn GitHub or Jupyter or MATLAB or a mouse, a keyboard, but try to teach them some basics about numerical methods. So the tools that I'm using are Jupyter with an Octave kernel. I use Octave just to show them, look, you don't have to pay for all of your software. And when you leave the university, you can still use these concepts that I'm teaching you. And then GitHub and then Kaltura is a video hosting software that UConn has a license for, and it just gives me a way of giving them some instant feedback. So who am I teaching? Again, mechanical engineers. At UConn, their average, the School of Engineering average SAT is 1298. They're required to have a minimum GPA of 3.5, which is, so these are driven students. They're very good. They're very good at the work that they do. And for the most part, they just don't do a lot of programming. They're not forced to do it. And so whenever they reach this computational mechanics class, a lot of them feel moderately interested in programming or MATLAB. And some are neutral, and then even more are uninterested versus very interested. And 90% of these students are seniors that are taking this class, and the last time they wrote code was when they were freshmen, and they took an introduction to computer science and engineering, and they slowly squeaked through the course until they decided, oh, I'm not going to use this anymore. This was very difficult. So this is what I'm trying to teach them in this course. So it's a senior level course. So Newton-Raphson method, so finding roots of nonlinear functions, optimization also of nonlinear functions. Ideally, they've had some kind of calculus, so they know how to optimize linear, or at least polynomial kind of functions. Some linear algebra, statistics, and curve fitting, and then also some finite difference methods. We don't get into finite element method, but we do some like heat transfer analysis and solid mechanics. This is what they hope to learn, at least what they hope that I'm going to cover. MATLAB. I'm just going to show them all of MATLAB. And to me, that's kind of funny because MATLAB, it's a tool, same as Python, same as R. You use it to accomplish some kind of goal, and yet it's kind of the topic that they expect this class to teach them, that they're going to be proficient experts. We're all doing this at the main campus in Storrs. It's the quiet corner of Connecticut. It's very beautiful, very serene. I've been very happy there for the last 2 years. We just bought a house, so we're very settled, very happy to be there. And why? Why would I try to teach these mechanical engineers that don't want to learn MATLAB and programming? And the reason, at least what I feel very strongly about this, is that engineering is inherently multidisciplinary. You can't create new products and new devices without dealing with electrical engineers and computer engineers, computer scientists, mathematicians, statisticians. And computing power is so cheap. We can put it in everything that we do. Our phones can constantly collect data. We can have our cars thinking about things that we had never thought about. Like, is that a pedestrian? Like, I'm not sure. So new mechanical engineering solutions, they require these predictive models, something tech-savvy engineers, people that are thinking a little bit beyond just pulleys and F equals MA. And I like this story because it's a very different view in engineering. When they were first building elevators in high-rise buildings, the complaint was they're too slow. They don't get me to my floor fast enough. And so engineers shrugged their shoulders and said, that's the biggest engine that we can give you. Like, we can't create more electromotive force with the power that you're giving us unless you want to invest in some new form of transport, like vacuum tubes from Futurama or something. So the solution was put a mirror in the elevator, and people stopped complaining. Now, they didn't change the speed of the elevator. All they did was distract the people so that now they don't have a complaint anymore. The same thing with driving, with transportation. When I was sitting on 84 and 90 coming into Boston, the traffic, it's not so much that I needed a faster car. My Honda Fit was going to do 30 miles an hour no matter what, no matter how hard I hit that accelerator or no matter how well I cooled my engine and what thermodynamics were going into it. So it's not really the solution that we need better cars, although I am a big proponent of thermodynamics and mechanical systems, so I would like to see faster and cooler cars because I'd like to see them driven, but just not in this situation. So the real solution is, again, something sideways. We need to just distract our users. Let the car do all the thinking and the frustrating communication and watching the road while we can use our phone, or I guess we could use a mirror. We could just put a mirror in front of our... So this is kind of what I think of the next mechanical engineer coming into the automotive industry or other industries, that they'll create these sideways solutions and work with new people. And I do some research with Pratt & Whitney. They're based out of Hartford, and they build airplane engines. And there's a lot of components that go into engines. And every single one of these components requires an advanced material model, mechanical models, statistical models of the data that's being produced from the actual implementation of this engine. And I work on these tiny little parts back here that are red, and actually not even the entire part. I just work on a coating on that part that's 100 microns thick. And meanwhile, this engine is a few meters long, and I'm just working on less than 0.1% of the engine. And yet my research takes up, I don't know, it could easily take up 40 hours a week of time of myself, or 100 hours a week of a grad student. And so you need all these kind of computational models, understanding of statistics, and mechanical engineering is not just F equals ma and energy is conserved anymore. It's also, how are you analyzing this data? What tools are you using for this? So this is how I'm teaching these courses. Hopefully you're convinced that mechanical engineers should know some sort of MATLAB or Python, or know how to use Jupyter. And so I'm using this Octave kernel, and I use an extension called Rise, and I'll show the link for that, but it's a nice way of taking my notebook and turning it into a presentation. And it's very quick, just a few drop-down menus. And then I use GitHub to host all of my documentations. And then also I enforce it. I tell them that if you don't do this, then you can't pass the course. But they have to host all of their homework assignments on GitHub as well. So they're not learning all of the details of Git, of like how version control works, but they're at least learning how to create a README file and how to put a JPEG on there instead of a screenshot of a graph that they created in MATLAB. And then Kaltura and Google Forms, these provide both the students feedback from my videos that have multiple choice questions, and then the Google Forms provide me with feedback on what are they understanding and what are they thinking about. And that's where I get these word clouds about, well, oh, I guess they all want to learn about MATLAB this semester. Traditionally, this is how I was taught and how I was used to teaching, was that usually the professor stands at the front of the class like I'm doing now, and I tell you my ideas, and then some people frown and hope that I don't ask them to use those ideas, and yet, sure enough, those ideas come back in the homework, and then they give me some resemblance of that idea back. So this is kind of the flow of information. It's that I give it to them, and then they obfuscate it a little bit and then hand it back to me. This flipped classroom, and there's lots of different implementations of this, but this is the way that I've decided to kind of use these tools to flip my classroom, is that instead of instead of teaching directly to the students, I record all of my lectures. So I create these Jupyter notebooks that are a combination of markdown formatting with actual equations and code that I execute during the video, and then they can see how I change that code on the GitHub. Or if they're good students, they might go and look at the versions and say like, oh, he had a typo back in like December 21st, but then he fixed it here. But no one has done that yet, not yet. But one day they will. So I post that online, and it gets them out of the class and watching on their own time. And this is one of the most positive things that these students seem to like, is that they can watch and rewatch this material whenever they feel like it. Like they feel like it's theirs now, like it's a YouTube video that they can say, hey, watch this, like the professor picks his nose at minute 3. And then both of us are putting all of our material onto GitHub into different repositories, but it's all one location where it's just a repository, and we're not doing a lot of version control and collaborating. We do a little bit of that in kind of the end of the semester project, and I do it for their grades. I show them like, this is where you went wrong, and I give them some suggestions that maybe one day they'll use. But then we both meet. We're still meeting in the classroom, but now instead of doing lecture material, me telling them what to do, they're there with homework assignments. And it takes care of a lot of the little bugs of like, what's the difference between a semicolon and a comma? Or why is this a parentheses? And what's an anonymous function? And these kind of simple questions that maybe 10 people have, but they thought that it was kind of a dumb question at first, but now everyone's having the same problem. So it's a nice way. This is, again, a lot of people are flipping the classroom, and there are different ways of implementing it. This is just one success story with Jupyter and GitHub. So this is that RISE extension, this Jupyter extension. So you can see, and this is from this GitHub repository. I'm not a contributor, but I do like it a lot. So I would suggest you check it out if you want. But it's just showing you how you can take a Jupyter notebook and quickly turn it into a presentation. And I'll show you. So here's my GitHub page, and it's on our enterprise server at UConn, but it is public, so you can go to this URL at the RCC 02007 F2017. And it has all of these different IPython notebooks. So here's round off and truncation error, and I can open up the Python notebook, and then once it loads up, it renders a mix of code that I've executed in the video, and also if I've updated it during class, then it'll show those results as well. So the students have access, they always have access to these notes and all these changes. And so then I also wanted to show like one of the assignments that they turned in. This was extra credit. I told them to find a bar with a dartboard and throw darts. They put up a polar coordinate plot. I stapled it to the dartboard, or maybe just use a dart, and then throw darts at it, and then send me the data, like post all that data onto GitHub. So here this student, one of I think 25 or 30 students that did this, they're posting the radius and the angle, and then so here, this is my Jupyter notebook of presenting their data back to them and looking at statistics and Monte Carlo models, so how do random numbers work. And these drop-down menus here, this is the RISE extension to actually turn these cells into slides, and they can either be slides or fragments. But what you get is this. Usually the basic interface is good enough for me, and I think it looks professional and nice. So just some questions like, how do we describe, what is a mean? What is a standard deviation? How does this describe your data? And then I can show them, look, this is how all of you hit the dartboard. So you're kind of getting close to 0, but you're at the bar, so it's plus or minus 5 centimeters. And then we can go through and say, what was the mean x position? What was the standard deviation? Again, plus minus 4 centimeters. Not terrible, it's pretty good. But it was also confined because it's only an 8.5 by 11 sheet of paper. And so when we see the y direction's plus or minus 5 because the paper's bigger in that direction. But, so where did they hit this dartboard? And then we can talk about, okay, here's the histogram of all of your hits. We can look at n equals 2 versus n equals 1, and the x and the y, and even show, hey, look, it's a Gaussian in 2 dimensions, and this is how you can analyze and visualize data. And so they can watch this both in a video, or they can go to GitHub and kind of go step by step. And to them, they see this notebook as a rendered kind of as a web page, and then in the video they see it as an interactive lesson. And here I'm showing a video of errors and numerical errors from round off versus numerical error, or sorry, round off and truncation error, sorry. So truncation error and round off. And when they're taking this quiz, so it starts off saying, hey, you're going to take a quiz, and then at points 1, 2, and 3 in the video, it asks them some question, like what is the 32-bit versus 64-bit version of pi, or exponent. And then finally it tells you, hey, you got 100%, nice job. And if it was wrong, then it would say you got a 66%, and this is the question that you got wrong. And at first I wasn't giving them the answers, it just gave you a score. And every video had 50 questions of like, hey, how come this answer is wrong? But giving some kind of instant feedback gives them some sense of like, okay, I'm on the right track. They feel better about it. Helps them, even though these aren't great, it's not graded, it's just telling you this is what you understand. So like I was showing before, all these notes are hosted on GitHub, and so they have access to them, and it also forces them to learn how to use GitHub because that's the only place the notes are. And so with these videos, and how are we doing? Good. So with these videos, what I found interesting was that 65%, so they're required to watch the video, but if they skip ahead, then it shows them, then it would show that they didn't watch the whole video. So if they're skipping through, then they didn't watch it. But 65% of the class is actually watching the entire video, which I was kind of surprised because usually in lecture, I'd say 30, like the other half, the 35% is actually absorbing the whole lecture, maybe less, maybe 10% is actually absorbing and interested, and the others are kind of nodding in and out, skipping ahead, just through sleep, time travel. And then 20% of the class is actually watching it more than once. They're going back and rewatching this. This is not something that I told them they had to do, nor do they get extra credit for it. They're just rewatching it because they have access to it. So it's not so much that the student's falling asleep because they're not interested. They might just, they're probably busy. They're on the lacrosse team. They're in a fraternity. They're also hosting, I don't know, baking club on Saturday. They're busy, and sometimes 10 a.m. on a Wednesday is not really the ideal time to learn about what machine epsilon is. So then I thought like, oh, they're watching these videos, they're so into it, there must be some trend of them like understanding more. But there's not. It's kind of random. But one thing that it did get out of this with these box plots, so this is showing the average score on these tests, and then there's always between 0 and 100%. Someone always scored 0. Actually, no, there was one. This must have been really well done. I must have really nailed that video. But there are two videos where they really understood it. But the average is always more than 50% or 50% or more, but usually the multiple choice questions are 4 answers. So they're not randomly guessing. which is good. They're at least making progress and understanding. And you don't get to redo it. They don't get to retry. So this is the first time you've seen the material, you're asked a question about it, and you're like, I don't know, B. No, sorry. But they are paying attention. And so one of the things that, so the hard part really is kind of getting them used to MATLAB, this MATLAB Ghost. And again, I use Octave, but it's all the same syntax. Getting them used to getting something done in MATLAB. And I spend about 3 weeks just telling them how to use MATLAB, how to create a function. And then I've also mixed in GitHub, how to post your code and how to document that code into a homework assignment. And within that first 3 weeks, at first, on day one, 90% of the class said that they don't want to use MATLAB. They're either not interested in it, they don't like it, something about it kind of scares them. But 3 weeks later, now that might sound like a lot of time if you're considering like a day-long workshop, but it's only 3-hour increments, so it's only three hours per week. Well, less than that, 3 hours minus 10 minutes per class, so 2.5 hours a week. And I don't have their full undivided attention the whole time, but within that 3 weeks, they're all ready to at least do the tasks that we've done in class. Not all of them, some are not at all ready, but that's only 5%. But most of them are at least ready to do what we've looked at, and then more than not ready are actually ready for something harder. And we're not even getting into something harder in the course. We're only going to use the core tools that I've taught them in that first 3 weeks. So some of the things that I've gotten from this experiment is then this is actually for me it's been a great use case for Jupyter because I can mix both my notes from the textbook, code that I can execute within a video, and the students can have access to that later. So it provides, with these videos, it provides notes, examples, presentations, so with GitHub and Jupyter all in one place, which is nice for the students to be able to go to one website, and then also the same website, that's where they're posting all of their work. And it's not just like a Blackboard kind of website that you only learn for school and then you don't use Blackboard in enterprise or any other kind of outside position, or even further on in academics unless you're actually an academic teaching a class. But then these students, they're watching these videos, they're watching the video and then they're watching it again and double checking their work, and they're going to GitHub and they're downloading my code and checking. Some of them have even brought up there's typos in my code, say thank you. And one or two have actually posted an issue to say, hey, this is what you need to fix, which is good. Usually that's the end of the semester, it's extra credit if you post an issue on your project and you fix it. But I can use the class time just for troubleshooting, so helping them get to solutions and work on things together. So it's a very versatile tool set, and it's scalable. I can, especially since I'm using a GitHub server to post these notebooks and they're just kind of viewing all this as a repository, I could send these videos out to, instead of 100 students, 1,000. And the difference would just be kind of how many people I can really interact with in person. So just from these first couple semesters using this, well, one semester really testing it out, seems like 30 people is about where the max is. If it's over 30 people, it's tough to get to their questions. They feel frustrated that like you were over there answering someone else's question when they were stuck and now they've given up. Now they're on Facebook, or no, they don't use Facebook anymore. I don't know what the next website is, but it's not Facebook. I know that. And so another lesson is just keep providing as much instant feedback as possible. So every time they need to, they can click a button and it says you're right or you're wrong, or this is the answer and that's not the answer. And that helps them, at least getting used to some of the software. It helps them feel like they're making progress, to have that almost like a gamifying, like, oh, they're leveling up. Like, And so some of the future work that I'd like to put together is have Jupyter, like implement a Jupyter hub and auto-grade some notebooks. So continue to provide more feedback for them. And then we can use the in-class time to actually do iteration. And again, that one of the things that came up was how do you combine that storytelling and the those ABC choices. And this is a nice way of doing that, is that you can work together on a new solution, and then out of class you get that instant feedback so you feel like you're not lost. And then also our engineering department is migrating to Python, so a lot of this is going to move into Python. But the core concepts are still there. You're still looking at statistics and it's still the same functions, just different syntax. And one of the possibilities is creating some shorter courses, or maybe a series similar to like a Coursera massive open online course or something like that. But with that, I'll answer any questions if there are.